Meso compounds. You have a meso compound whenever you're dealing with a molecule that contains multiple chiral centers. So that's definitely a requirement. There must be multiple chiral centers present in the molecule. But in addition to that, we're going to find out that there is a symmetry element present in the molecule, specifically a mirror plane. So take a look at the following molecule, this diol, specifically 1, 2, 3, 4, 5. So this is pentadiol. The carbon to which the hydroxy group is bound is actually chiral, and that's true for both of the portions right here. This carbon is chiral, that carbon is chiral. So this is penta 4, 2,4 diol. And looking at the first carbon right here, priority 1 goes to the oxygen because that is heavier than carbon. Priority 2 goes to this segment because this is a CH2, and CH2 wins over CH3. So we have our three priorities. So this looks like an counterclockwise rotation, an S configuration. Since the hydrogen is technically pointing away, this is indeed an S configuration. Down here for this chiral carbon, oxygen is priority 1, priority 2 goes to CH2, which wins over CH3. So this looks like an S configuration, but because the bond here is dash, the hydrogen is pointing at you. So even though it looks S, it's in reality R. Okay, so we have the 2S for our configuration for this particular molecule. All right, now if we draw the mirror image, which is to say that you copy and paste this molecule and simply change the dash bonds to bold and the bold bonds to dash, right? So you just alternate the sequence. You are in essence changing the configurations, and these are the enantiomers of each other. And because we have two chiral centers, we have 4 possibilities for isomers, right? So all I'm doing right here is alternating. I'm keeping everything the same except for the methyl on top, which I'm changing to dash when comparing these two molecules, top and bottom. And over here, I'm keeping the everything the same except for the methyl on top. So going across, the two molecules on the bottom are enantiomers of each other as well, right? I changed the configuration. 2R became 2S, 4R became 4S. All right, now let's go back to the original one right here. 2S became 2R and 4R became 4S. But there's one tiny little issue. At first look, this seems like, yeah, they are totally enantiomers. You know, we changed the dash bonds to ball bonds and the dash bond and the ball bonds to dash bonds, right? So it looks like, yeah, we got the enantiomer. But the thing is this, if you start from the top to the bottom, notice what happens. We have carbon 1, carbon 2, carbon 3, carbon 4. So oxygens are positions 2 and 4. But if you start from the other end and make this position 1, then that's position 2, that's position 3, and that's position 4. And once again, oxygens fall under positions 2 and 4. So what this means is that, and notice what I did right here, I just rotated these bonds so that I put the hydroxides next to each other. What you see right here is that, technically speaking, there is a symmetry element in the molecule. There is in essence a mirror plane that crosses through that CH2 across, and the molecule itself has the mirror plane within the middle of it, because this OH is reflected with that OH, this dash methyl is reflected with that dash methyl, and so is the CH with that CH. Because there's a mirror plane, what this is telling you is that this molecule cannot be chiral, because for you to have a chiral molecule, mirror planes and inversion centers must be absent. And the fact that a mirror plane is present in this molecule that has multiple chiral centers means that the entire molecule is achiral. It does not have a chirality overall. It's not a stereoisomer, in other words. And so these two versions, you know, basically taking this molecule, copying, pasting, and changing the bold bond to dash and the dash bond to bold, does not equate to an enantiomer because of the presence of this mirror plane within the molecule. And in essence, this is the same compound. Now, the trippy thing about it is that both compounds have chiral centers, and yet the entire compound is not a stereoisomer. And because the two of them are the same compound, we don't just say that they are just the same compound. They do have chiral centers, so we refer to them as meso compounds. So technically speaking, these two are the same compound. These two, on the other hand, notice that S becoming R and R becoming S, you can easily flip those numbers, and so you end up with the same thing. But R becoming S and R becoming S, in other words, you have RR turning into SS. There is no way whatsoever that you can tune RR into SS or SS into RR. So these two molecules are different from each other. They are not the same thing. Um, so altogether you have three isomers, and this diagonal shows you the diastereomers. These two molecules are diastereomers of each other. The molecule on top and the molecule on the bottom are also diastereomers of each other. And of course, the ones that were across are enantiomers, but in the case of the top molecule, we have a meso compound because of the presence of that mirror plane within the molecule. So just be aware of those molecules. Whenever multiple chiral centers are present, you have to be careful to identify, whether there is a mirror plane or not. Because if there is, the thing that you would call an enantiomer is actually the same molecule, and together they represent meso compounds. Okay, so that covers it for stereoisomers. This was a big topic. It's the first time that you're looking at molecules from the point of view of where the bonds are located in space. So this will take a little bit of practice on your own by using the methods that I taught you in this lecture series. I think I'll help you make this daunting task a much more manageable task. In any case, feel free to contact me if you have questions, and I will see you in the next lecture series. Bye bye.